Welcome to the Explainer. Today, we are tackling a core geometric challenge that sits right at the very heart of machine learning. How exactly do we fit curves to messy, complex, real-world data? We're going to break down an incredibly elegant solution from Andrei Burkov's 100-page machine learning book, and honestly, it's going to completely change how you view data modeling.
It's a fundamental question, right? In our early machine learning journey, we all start with linear regression. We learn to draw that neat, straight line through our data points. But let's be real, reality rarely walks a straight line. So what exactly do we do when our dataset totally ignores our attempts to draw a straight line through it, and instead curves, dips, and zigzags all over the graph?
Section 1. Beyond the straight line, the limits of simple models.
A straight line is rigid, and when the underlying phenomenon you're trying to predict is fluid and complex, well, rigidity is your enemy. Now, you might be thinking, hey, just use polynomial regression, and you'd be absolutely right, up to a certain point. If we have a simple one- or two-dimensional dataset, we can easily toss in some squared or cubed terms to bend that line. But we live in high-dimensional realities. The book points out a pretty harsh truth. If our input is a feature vector with more than 3 dimensions, finding the exact right polynomial equation to fit the data becomes an absolute nightmare. The math just gets way too convoluted.
Which brings us to Section 2. Meet Kernel Regression, the elegant solution. When simple lines fail and high-dimensional polynomials become impossible to manage, we need a smarter approach. Okay, let's dive into this. Kernel regression is what we call a non-parametric method. This is a profound shift in thinking. It doesn't mean there's no math involved, but rather that there are no fixed parameters. There are no standard weights and biases for the model to learn and lock into place during training. Instead, the model is based directly on the training data itself. It's conceptually very similar to the k-nearest neighbors algorithm. You are effectively letting the data act as the model.
Section 3. A data-driven model, looking under the hood. So if there are no parameters to learn, how exactly does this non-parametric method calculate a prediction for a new, unseen piece of data? The logic here is beautifully simple. Our prediction, represented by f of x, is essentially an average. It's a weighted sum of the target values, those yi's, from the data points we already have. Imagine every single data point in your training set gets a vote, aiming at the target prediction. But, and this is absolutely critical, those votes carry different weights based on how relevant they are. So the big question is, how do we calculate those weights?
Section 4. The Gaussian kernel, weighting the data.
The mathematical engine driving this entire operation is the kernel function. This is the mechanism that determines exactly how much influence, or weight, each existing data point gets when predicting a new one. The most frequently used is the Gaussian kernel. Now, what's really interesting about this slide is what it does practically. It assigns higher weights to training examples that are physically closer to the new input we are trying to predict, and lower weights to those further away. But the absolute secret sauce here is its hyperparameter b. By varying b, we dictate how rapidly that influence drops off, which dramatically shifts our resulting regression line.
Section 5. Tuning the hyperparameter, finding the sweet spot. Because kernel regression doesn't learn standard parameters like a traditional algorithm, our primary job as data analysts becomes finding the perfect value for that hyperparameter b. It's all about finding that sweet spot where the model performs optimally. So how do we actually do that? Well, here's the precise workflow. First, we choose a candidate value for b. Second, we run our model, using that b, on a validation set. Notice I didn't say the training set. We use a separate validation set so we can see how the model generalizes. Third, we calculate the mean squared error to see how far off our predictions are. And finally, we adjust b up or down to minimize that error.
Section 6. Finding the perfect fit. Visualizing success.
This step-by-step tuning is absolutely vital, and we can easily see why when we visualize it. Let's pull back from the abstract mathematics for a second and connect this to what it actually looks like on a graph. If your b value is tuned poorly, say it's way too small, your curve is going to zigzag wildly. It will try to hit every single training data point perfectly. That is a strong overfit. Sure, it looks flawless on your past data, but it will fail completely when predicting the future. Now, if b is too large, the line becomes too stiff and underfits. What we are really hunting for with our validation set is that good fit, a smooth curve that captures the true underlying trend without memorizing the random noise.
Real quick, before we wrap up, here's a fun fact straight from the book's conclusion to show you where you can take this knowledge next. If you find the flexibility of kernel regression appealing, you should definitely look into Gaussian processes. It's a competing supervised learning method that does something quite magical. It actually provides confidence intervals for the regression line at every single point. It tells you not just the prediction, but how mathematically certain it is about that prediction. Pretty amazing, right?
But for today, take a step back and appreciate what kernel regression accomplishes. Instead of forcing your data into a rigid, predetermined mathematical equation, you are empowering the data itself to define the contours of the model. It handles high dimensions effortlessly, it bypasses messy polynomial math, and when tuned correctly, it creates beautifully fitting curves. So I'll leave you with this question to ponder. In your next big project, are you still going to force a straight line, or are you ready to let the data draw the line? Thanks for exploring this topic with me, and keep learning.